The final speaker will be Daniel Arnold from AIUB Bern. The title is Systematic Errors in Satellite Laser Ranging Validations of Microwave-Based Low Earth Orbiter Solutions.
Please excuse, it's not Daniel, it's me again. The main author, Daniel, could not make it to Guadalajara, but I will do my best to present his slides on this systematic errors in SLR validations of orbits that were actually determined by microwave observations. So the talk is closely related to what we just heard. Well, you all know that we have many observations, not only of the geodetic satellites, the cannonball satellites, but to active satellites that are also equipped with GNSS receivers or DORIS instruments. And there the main determination of the orbit is based on these microwave observations, and SLR is used for orbit validation. And I just want to remind you, SLR does not only provide information in radial direction, but due to lower elevation observations, also a long track, cross track, so a real 3D validation is possible. The requirements on orbit accuracy are very high meanwhile. So GGOS formulated requirements on reference frame with accuracy of 1 millimeter and stability of 0.1 millimeter per year, mainly to observe sea level rise. And of course, these requirements, they translate into requirements for satellite orbits, in this case of altimeter satellites. So yes, we have to be careful, we have to do a good job. And we know that in SLR we have errors. Our observations are great, but we have biases. And the normal thing we do is, when we do orbit validation, we focus on what we believe well-behaving stations with little biases and throw away all the rest to get nice residuals. That's a pity. So the idea is to reverse the process. Meanwhile, we have very high quality orbits based on GPS observations, for example, microwave observations. These satellites, they are active, so they have a controlled attitude. So therefore, also the SLR observations of these satellites benefit. We have less satellite signature effects. And we have many observations of these satellites. So why not use these observations to estimate station corrections instead of just validating the orbits? So the first step is to compute GNSS-based orbits of these satellites, Sentinel-3A and B, 6A, then the 3 swarm satellites, ABC, like we saw it before, the 2 Grace follow-on satellites, and also JSON-3. These are our main information input. We fix these orbits, then we compute SLR residuals, and we apply, the best of models that we have. For example, these reflector characteristics. We take the station coordinates from SLRF 2014, and in the end I will also show you some slides based on SLRF 2020 to see the differences. Then we apply all the state-of-the-art corrections like the range biases we get from ILS standards. And it stopped working. Oh, okay, there it is. We do an outlier rejection. So we have a threshold of 20 centimeters for the SLR residuals, and we have an elevation cutoff. So we throw away low elevation observations because they are noisier. And then, based on these orbits, we compute, based on the GNSS orbits, we compute partials of parameters of interest to us. For example, the station, ranging, or timing biases, or coordinate corrections. And solve the whole system based on the SLR residuals. And if you are more interested in this topic, please take a look at this paper, the Arnold 2019 et al. Satellite laser ranging to low Earth orbiters, orbit and network validation in Journal of Geodesy. The whole thing was triggered by a bias study in the Copernicus POD Quality Working Group. There we have 3 different analysis centers providing their orbits, all based on different software, so they are independent orbits, and they were used to estimate station range biases, yearly ones, and here I have example for one station, 4 yearly biases, and they are not perfect, but they show some agreement, especially when co-estimating station coordinate corrections. And so yes, we believe we can estimate station corrections from observations of active satellites. But well, at the moment we introduce our orbits as perfect. That's not true. We have also orbit errors, like incorrect center of mass locations, incorrect offset vectors of the microwave sensors or the laser reflectors. Of course, also deficiencies in the force models. Do they play a role? So let's test it. So we fix 11 of the best behaving SLR stations and instead estimate orbit corrections from the SLR residuals. So we shift around our orbits of these 6 satellites here in a long track cross-track radial, and the values that we estimate are not 0. So yes, there seem to be orbit errors involved. Do they play a role? So let's repeat the experiment. Estimate station corrections, coordinate corrections in east, north, up, and range and time biases for a number of stations with the original orbits, and then with the orbits that were corrected with the corrections that I showed in the slide before. Compare the results. What a pity, the numbers are different. So obviously these orbit errors, they do play a role, so they affect our station corrections, so we have to consider them. Now the optimal thing would be to co-estimate station corrections and orbit corrections in one estimation process. But what a pity, we have correlations between different sets of parameters. For example, range biases and radial orbit offsets are highly correlated. There are more correlations. All these rectangles that you see in the correlation matrix to the left indicate this type of correlations. It's not that easy, so we have to introduce constraints. We can do so. We have a number of physically meaningful constraints, zero mean constraints, or no net translation, no net rotation, no net scaling constraints that we can apply. And we made different tests, estimated station corrections here for the Zimmerwald Observatory. And these are results. How can we validate these results? Well, we can compare with local ties. We can take the coordinates from the ITRF and SRF frames, compare to the geometrically measured local ties, and then we get a shift of 0.5, 2.9, and 7.7 millimeters in the 3 axes. Comparing to the values that we estimated, applying constraints, they are at least in the same range. So we are optimistic that our station coordinate corrections are meaningful. And let's have a look at the residuals. These are the residuals from 32 SLR stations to these 9 satellites before adjusting the orbits in the stations. And this is after. So the RMS drops from 14 to 9 millimeters. So we can really improve the SLR observations, applying a number of meaningful corrections, estimating a limited number of parameters. And I think it's worthwhile the effort, because SLR observations are expensive and very precious. We should keep them, not throw them away in orbit validation. This was all based on SLRF 2014. I will now, my last 3 slides, repeat this with 2020, the preliminary frame provided by the ILS for test purposes. We did not recompute the orbits, just recomputed the corrections in the new frame. And you always see 2 numbers for each station in this station coordinate corrections, left with 2014, right with 2020 reference frame. And whenever it's green, then the 2020 corrections are smaller. So I would say this looks promising. So somehow the consistency in the 2020 reference frame seems to be better than in the old reference frame. Now we also estimated the range biases, left old, right new frame, and they're pretty consistent. So our interpretation is that with this approach we are able to separate effects on the station coordinates from effects on the instrumentation. So the range biases really catch up something in the instrumentation of the observatories, not the coordinates. So they're independent on the station coordinate realization. And finally, we estimated the orbit corrections. Again, left, old, right, new reference frame. And they're also pretty much consistent. So also there, we believe those parameters really catch up something in the orbits that is satellite specific, not depending on the reference frame. So let me conclude. Oh, no, I forgot. Finally, let's look at the residuals. And if we look at the residuals before adjustment, it doesn't look nice for SLRF 2020, but after adjustment, we see a small improvement. So also this indicates that SLRF 2020 actually a good job was done. It's a gain in consistency. So let me conclude. The numerous SLR observations to active LEOs have the potential to be used for the determination, monitoring, and calibration of systematic station errors. Systematic orbit errors affect those station parameter estimates and should be taken into account. But when co-estimating, constraints are needed for the decorrelation. And the preliminary SLRF 2020 looks very promising. Generally, smaller coordinate corrections are achieved. And the range bias and orbit offsets estimates seem to be consistent, so they do not depend on the SLRF realization. That's it. Thanks for your attention.
Thank you, Uri. Any comments or questions to this talk? Nothing online? Okay.
You mentioned there that the SLRF 2020 looks very promising. I wonder how you used it. Did you use just the a priori coordinates, or did you also use the biases that we estimated on top of?
Your set of mass corrections, you mean? Or?
No, the estimated biases.
From the data handling file. At least I gave it to Daniel, so I think he applied them. But to be really sure if everything was applied, please ask Daniel. He did the actual computations. He's the expert.
Okay, thank you very much.